classification Chomsky did. It's called the Chomsky hierarchy. And he defines grammars as extensions of each other, the same way that we define finite state automata is a subset of PDAs, which is a subset of Turing machines. So you can do the same hierarchy, a similar hierarchy in grammars. Okay? Context-free grammar is one type of that hierarchy. Okay, first of all, you have the general grammar. What is a grammar? Okay. As we said last time, you have a set of terminal symbols, right? This is the alphabet. If you use the grammar as a language recognizer, okay? The strings are made out of those alphabet symbols. Okay, so you have, the alphabet of course must be finite because we have limitations because of this machine, it's Boolean machine. Then what do you have? You have the non-terminal symbols. For example, here is a rule. A verb is eat or sleep. Okay? This is a terminal symbol. That's part of the language. Okay, and this one. But this one is an auxiliary symbol. It defines a set of symbols as belonging to some category. That will be a non-terminal symbol. So when I put strings together in a language, I can say the cat eats the mouse. Suppose I have noun, right? Cat, dog. Okay? I can say the cat eats the mouse. You know, adverb. What is that? Okay. The cat eats the mouse is in the language, but I cannot say the noun eats the mouse. And noun is not. So you have the terminal symbols. The strings are made of those. And you have the non-terminal symbols. They're just used in the rules to define a structure in the language, the syntax of the language. Together, both of them are called the vocabulary. Okay? Because if you open the dictionary, you know, the English dictionary, he also defines noun, even though it's not. Okay? So the vocabulary is both the terminals and the non-terminals. What else you got? You got a set of rules. They're called production rules or derivation rules. Okay? What do the rules look like? You can have the left, or they're called substitution rules. Okay? And basically what the rule says, if you see this sub-expression in a string, you can substitute it by what is on the right side. It's a substitution rule. What can you substitute by what? On the left side must be in here. Well, what does it mean? You must have, V star is anything. You can have anything you want. The only constraint on the left side is what? You must have at least, N stands for the non-terminals. N is the non-terminals. It's the vocabulary minus the terminals. So, in a general grammar on the left side, you must have at least one non-terminal. You cannot have all alphabet symbols. This is not a legal rule. You know. Cat eats. You can substitute this by dog eats. It might look legal, but it's not legal because these are all alphabet symbols. You change the meaning. You cannot substitute cat eats by dog eats. That's not different. You change the sentence. Okay, so you must have at least one non-terminal here. On the right side, V star, you can have anything you want, including the empty string. Okay. Okay. One of the symbols, of course, the non-terminals is called the starting symbol. Okay. Here is an example of a grammar. Left side, at least one non-terminal in every room. Okay. It's a grammar. A string in here in V star. Could be terminals, non-terminals. You see, this string generate. Let me go there. You cannot see that, right? I'll do that. Okay. If you have a string X and a string Z, you say that the string X directly generates Z if with one substitution rule, by doing one substitution rule, you can produce Z from X. Okay. For example, well, we lost the grammar. If this was the grammar, right? Is it true that S directly generates C? Yeah, one rule, I got it. Is it true that S directly generates ABS? Yeah, sure. With one rule, I got that. Is it true that S directly generates AB? No, because you need two rules to do that. S goes to ABS, and then you take this expression, and S generates AB. So it's true that ABS directly generates AB. So you must do it in one step. Okay. Well, if you can generate AB from S, then you call that in a sequence of steps, more than one step. You call that the closure, the transitive closure. So X generates Z. Okay? In more than one step, you say Z is in the transitive closure of X. You can start with X, apply rules, get Z. Okay, now, what is the language recognized by the grammar? They give you a grammar, what's the language? All the strings in sigma star you can get by starting from S and applying a sequence of derivations. Okay? Which means all the strings X you can get. So it's the transitive closure of S that is inside sigma star, intersection sigma star. All the terminal strings you can get from S by applying a sequence of rules. That's all. Right? If they give you a grammar, is it easy to figure out what the language is? So who are those strings you can generate from S? Sometimes it is, sometimes it's not. Like when you go home, I'll skip this. Go and look at this one and say, well, what's the language generated by this grammar? It's not so easy, you know, you got to spend a few minutes thinking about it. Okay. And you might be able to figure out the language. So at this point, we don't have an algorithm. What's the language? It turns out in this example is, I think, XX. X squared, where X is any string squared you can generate, where X is any string. Yeah. You can generate any string of binary symbols, like 0, 1, 0, 1, fine. 0, 1, no, you cannot generate that, because it's not in the form X squared. Now, in the case of finite state automata, right? If I give you a finite state automata instead of the grammar, or if I give you a right linear grammar, and I ask you what's the language, you can take the right linear grammar, you have an algorithm. You can describe the language as a regular expression. Okay, so I have at least a way, I don't need to think hard, I automated the process, boom, he pops out the regular expression. Okay. But in general, there is no algorithm. If I give you a general grammar, ask you what is the language recognized by it, defined by it? There is no algorithm to do this for a general grammar. One question is there such an algorithm? Maybe we don't know it now. Right? Can somebody, some smart guy, okay, he can go spend 2 days, he comes up after on Friday, says, I got an algorithm. Give me any grammar, boom, I'll give you the language. It turns out such an algorithm does not exist, and you can prove that. But we will do this later. This is a non-computable problem. You can prove you cannot do this. Don't try. You'll waste your time. Okay, now there are, besides the general grammar, all the grammars in the world, and there is infinite number of grammars, right? Okay. Even if the alphabet is finite, let's say 0, 1, this is the alphabet. How many grammars you can possibly have? Infinite number. There are some types that Chomsky defined. Chomsky is this linguist that does computational linguistics. He's at MIT, he's very old. Okay, type 0 grammar. What is a type 0 grammar? It's a general grammar where every rule has this form. Now, what is the form? Well, in every rule, the left side must be in n plus. What does that mean? And the right side could be in v star. So the right side could be anything, right? V is terminals, non-terminals, starred, any possible expression. So the right side could be anything you want. We don't care. But to be type 0, the left side must be what? What does it say? Huh? What? Right. And at least one. It cannot be the empty string go somewhere. You cannot substitute the empty string by something. Okay, so the left side should be a string of length at least one of non-terminals. As we said, just non-terminals. You cannot have, if the alphabet was AB, if you have a rule like this, again, our notation here is what? Lowercase is in the terminals, uppercase no non-terminals. I cannot do that. This is not allowed. So that's type 0. We can skip this. We're not really going to do anything with context sensitive, with erasing. Context sensitive grammars are very bad. We have very few algorithms for them. What does context sensitive mean? Basically, it means a certain quantity you can substitute with another quantity based on the context, based on what's before it and what's after it. Natural languages, almost all natural languages, I don't know all of them, so I cannot say all. Let's say English and Greek or whatever, or Spanish, they are context sensitive. Okay? Take the symbol go. Go, go. What does it mean? Well, I don't know. It depends how you use it. I go to the market. If I is in front of it, the market is after it, this means walk there or something. Get there. I play Go with my friends. Oh, now it means the game, the board game. So it's context sensitive. You cannot look at the simple no, or even substring, a whole substring. Okay. Okay. He is tall. What does that mean? I don't know. What's in front of him? I don't think he is tall. Oh, now this means he's not tall. Okay. But if in front of it you have, I believe he is tall. Oh, yeah, he is tall. Those are difficult. In programming languages are not like that. X plus 1, what does that mean? Well, it doesn't matter what you have in front of it or after it. You can have x plus 1 plus 3. Well, the x plus 1 substring is x plus 1. It doesn't matter x plus 1 plus 3 or plus 5 or plus z. Right? Equal. Okay. Some languages, the problem is when they overload an operator. If you have x equals 1, that's different than if you have the if in front of it. If they overload the equal. But that's a very special case of context sensitive that I can deal easily. In general, they're very difficult grammars. So let's skip that. We will not do anything with that. Let's go to type 1. Type 1, every rule must be in that form or that form. Also, we will not do anything with those. It's context sensitive. With erasing means that thing that can have many meanings, you have the option to erase it, throw it away. Yeah. This is context sensitive. So I'm going to skip type 1 also. We will not use it anywhere. Basically it says what you substitute the non-terminal A by depends on what's in front of it and after it. So I can have a rule, context sensitive, right? A non-terminal B goes to A, so you have to keep the left and right. And then I'm substituting B by A. And then I can have a rule. So basically, what you substitute B by depends on his surroundings. In one case by A, in the other case by B. It's sensitive, context sensitive. Let's go to type 2. These are the grammars we're going to do a lot with. Context free, type 2. Okay, what is type 2? What is a context free grammar? That's what we want. Okay, every rule must be in that form. What's the form? On the left side, you're allowed only one, exactly one, non-terminal. That's the big restriction. One non-terminal exactly. None of that stuff. The right side could be anything. No restriction on the right side. It's in this style. It could be the empty string, anything you want. Right? For example, this grammar. Is this context sensitive? Yeah, sure. I have two rules. S goes to E and S goes to something else. One symbol on the left. Okay. If they give you a context-free grammar, we'll do an algorithm where you can find a PDA that recognizes the same language. But if you want to find the language, what is the language? Like 3 A's in a row, I know. What is the language recognized by this grammar? There is no algorithm for that. Okay. But you can build a PDA, you can build a machine that will do it for you. So when you give a string, the machine will say, yes, it's good, or it's in the language, or it's not in the language. So that's all you need. So, but if you want to find the language and express it in verbally, like using English, you might be able to do that, you might not be able to do that. It depends how complex this is. In this case, it's easy, right? What's the language defined by this grammar? Well, all the strings I can get from S. Okay, and I can do a sequence of substitutions, or last time we said I can do what they're called derivation trees. Okay, so what can I get from S? Well, I can get E. Okay, E is in the language. What else can I get?
AB.
Well, if you use ever this rule, you're done. There is nowhere to go. So the other option is start using this rule repetitively over and over again. So the only other option is I can get ASP. Now, if I substitute with E, I'm done, and I have the string AB. If not, I only have one option. And I can get A squared, B squared, and so on. So what's the language? A, N, B, N. Okay. So that's type 2 grammar, context free. Let's go to type 3. This is called the linear grammar. Right linear, the one we did, is a special case of a linear grammar. Okay. What's a linear grammar? Every rule looks like, on the left, one terminal, one non-terminal. On the right, you cannot have anything you want. Either the right side is totally sigma star. In the right side, you either have 0 non-terminals, or if you have non-terminals, you must have only one. So what's the restriction on the right side? You can have at most one non-terminal. Then it's linear. Like this guy. That's a linear grammar. By the way, let's take this linear grammar as an example. Can you find what language it defines? It will define this. And you can easily check that, right? What kind of strings can you get? Well, if I start with this, right? Well, I can get E, that's in the language. Or otherwise, every time I apply a rule, whatever symbol I got on the left side, I'll get it on the right side. You apply a rule, same thing. You'll have a match, left, right, left, right. Maybe you can do the B. You'll have a match. Right? So what you're getting? You're getting the inverse of this guy over here. Okay? So you're getting, what's this? Is that the even palindromes? The even palindromes. So that would be a grammar to produce the even palindromes. Now let me ask you this. For the set of even palindromes, can you build a right linear, you know what the right linear grammar is, right? It's linear, it is linear, but we said a linear must have at most one on the right side. Well, if it has a non-terminal on the right side, it cannot be in between sigma star symbols. It must be the last symbol. So the non-terminal on the right side must be the last one. Then it's right linear. It's on the right. That's a special type of linear, but it doesn't have a number yet. Okay, let me ask you this. Take the set of even palindromes. Okay, in alphabet A, B, whatever. Can you build a right linear grammar for it? If I ask you, can you build a linear grammar, you say, yes, here it is. Yeah, there is a linear grammar for it. But can you build now a right linear grammar for it? What will you say? Should we try? How many hours you want? You want 2 hours? Or, no, why not? So for the set of palindromes, is there a right linear grammar that will define it? He said no. Why? Cannot match the last symbol? Why you said no?
We are growing only on the left side, right?
I don't know what that means, growing on the left side. Anybody? Let me help you a little bit. What did we do? You have to use the stuff we did so far.
Pumping
No. Yeah, pumping. First of all, let me ask you this. Even palindromes, is this regular? No. You can show it using Pampiliman, right? We did that actually. And we had to go to the second version, remember? Of the Pampiliman. Okay, let's call this language L. It's not regular. Okay, what else you know? That right linear grammars are equivalent to what? Regular expressions, or of course all of these things, like FSAs. Right? Right linear grammars, we have algorithms for converting a right linear grammar to an FSA non-deterministic. Right, so we also know that. Right linear grammars are FSAs. We know that this is not regular.